So today we're going to talk about solving a system of linear equations using matrices. Okay, matrices. So when you look at those things on the screen, those little square braces around all those little numbers in there, that is a matrix. Okay, that is called a matrix. So they define matrices by how many rows and how many columns they have. And so if you look at this first matrix, we have 1, 2 rows, and we have 1, 2 columns. So 2 rows by 2 columns makes this a 2 by 2 matrix. Okay, this is referred to as a 2 by 2 matrix. Now the other matrix example beside it has 1, 2, 3 rows and only 1, 2 columns. So it's a 3 by 2 matrix. And so the dimensions of the matrix that you will put, if they don't always show the dimensions by any means, but if they put numbers down there, that is what they're referring to, the dimensions of your matrix. Now looking further down here, we do have what we refer to as a system of equations. So when you look at part A, that is what they call 2 equations, 2 unknowns, meaning there's 2 equations and 2 variables, x and y. So each of these, part A and part B, is 2 equations, 2 unknowns, and part C is 3 equations, 3 unknowns, x, y, and z. So what we have to do is convert this system into a matrix. So the first thing you want to do though is to make sure that every variable is in every equation. So for example, in part A, we would want to put a 0x plus 5y equaling 12 in this example. I wrote that kind of small trying to fit it in there. But you would want to put a 0x plus the 5y equaling 12 so that you have every variable in the 2 equations. Then if you wrote it as a matrix, you would give your little square bracket things, and you would put the coefficients, the constants, in this matrix. So the first row you have a 3 as a coefficient of x, a -1 is a coefficient of y, and then on the end a 10 is a constant. On the next equation you have a 0 as a coefficient of x, a 5 is a coefficient of y, and the constant 12 on the end. This would be referred to as your augmented matrix for that system of equations. Now in general we would put a dashed line where the equal part of the equation is to kind of help define where the coefficients of the variables are versus the constant. Part B is kind of a mess, so I would go ahead and distribute this 3 and let this be 3x plus 3y and clean up the equation so the 2x plus the 3x is really a 5x, and then you have your 3y all equaling 1. The bottom equation, if you distribute this 6, this is 6x minus 6y, and you want your equations where the x's line up and the y's line up and the equal in the number, so you'd want to put it as 6x minus 6y equaling 14. So you would rewrite your equation in standard form before you would convert it then to the augmented matrix, which would be a 5, a coefficient of 5, coefficient of 3 and 1, 6, -6, and 14, and this would be your augmented matrix. Again, there's a tendency to put either a dashed line or something in there to kind of separate the coefficients from the constant. Your example part C, if you take a close look at it, you have the x variable, the y variable, and a z variable. So every equation you want to say something times x plus something times y plus something times z equaling a constant. So this first equation you'd say 1x given, but you'd put a 0y in here plus z equaling -1, so every variable is in the equation. The second example does not have an x, and so you'd let it be 0x plus the given 1y. Oh, hold on. That's not true. We do have an x, don't we? We have a 2x, and then we have a 1y. We don't have a z, so we would put 0z in there again so that every variable is in the equation. It's the bottom equation that doesn't have the x, so this would be the 0x, then the minus y, then the plus z equaling 3. So this is the same system of equations where everything is written in standard form, and you want it all written in complete standard form before you convert it to an augmented matrix. So the first row would be a 1x, a 0y, a 1z, and a negative 1. The second row would be a 2x, a 1y, a 0z, and a 5. And the third row would be a 0x, a negative 1y, a 1z, and a 3. And then, of course, you would put your either little dashed line in there to indicate the separation of your coefficients of your variable and the constant on the end. Okay, so those are called your augmented matrices for each one of these examples. So you might see that word augmented matrix in your homework, and that's what we're doing. Now, here are some examples of some augmented matrices, and they want you to convert it back to the equation. So if you look at this first row, you have 1, 2, 3 terms. So that means you have an x, a y, and a z variable. So if I converted this to an equation, this would be 1x, 0y, and 0z equaling negative 3. So if there's 3, well, if there's 4 columns, there'd be three of the terms would be your variables x, y, and z. This one would be 0x plus 1y plus 0z equals 0.05. And the last row would be a 0x, a 0y, a 1z, and a 12. So if your matrix is set up like this one, where the diagonal is all 1s and all the others around it are 0, then this would be your equations, which ultimately would be just x being negative 3, y being 0.05, and z being 12, which is actually the solutions, because those are the values of each variable. So this form of a matrix is a good form to be in because it gives you solutions to your system. We will later find that this is called the reduced row echelon form of a matrix. That's a desirable form to be in because it gives you the values of the variables or the solution. Part B, you only have 2. You have an x coefficient and a y coefficient. There's no coefficient for z. So this is just a 2-variable equation in each row. Okay, so converting it back out of the matrix to linear equations, this would be your system. And it's actually pretty nice itself because if you solved it for x very quickly, you would get x equaling 1/6, and then you could come back and get your y. So that's not too bad a form of the matrix either. Okay, so what's interesting about matrices is we can do these things, these operations on them, meaning we can add, subtract, and multiply and even divide by using what they call row operations. So we're going to do some basic examples to try to understand the notation and how to perform these operations. One of the things that we can do is we can interchange rows. And the way they notate that, as you see in red here, it says, well, let me change. Come back, pen. Okay. This is row 1, and this is row 2. Okay, now their row 1's and row 2's notation, they use a little more of a, they use a subscript number instead of right in front of it. That's their row 1 and their row 2. This kind of double arrow is the notation for exchanging the elements of 2 rows. So if we exchange the elements, that means bring the bottom row up to the top and move the top row down to the bottom. So that means exchange 2 rows, and you can exchange rows anytime you want to, and that would be how you would notate it. Okay, example 2 says multiply a row by a non-zero constant. All right, so what they're doing here is they're saying come in here and take row 1 and multiply it times 3, and take those results and put it back in the row 1 position. So take all the elements of row 1 and multiply it times 3, and put those numbers back into the row 1. So what you need to note here is that the only row that's going to change is row 1. Row 2 will not change. So when you come back to write the resultant matrix, it's sometimes good to go ahead and write the row that does not change. Now, if I take 3 times row 1, 3 times 3 is 9, 3 times 2 is 6, and 3 times negative 5 is negative 15. Okay, next example. Add a multiple of one row to another row. So what they're asking me to do in this example is take 2 times all the elements of row 1, take those numbers and add it to the numbers in row 2, and after you've done that, those results will be the new row 2. Okay, so after I've done all they want me to do, row 2 is changing, not row 1. So row 1 remains the same. It's only row 2 that ultimately whose numbers will be different. Okay, so let's do what it's asking me to do. 2 times row 1. 2 times 3 would be 6. 2 times 2 would be 4. And 2 times negative 5 would be negative 10. Take those numbers and add them to row 2. 6 plus 1 is 7. 4 plus a negative 2 is 2. Negative 10 in my handwriting plus 10 is 0. So now we have done what it asked us to do. Multiply every term in row 1 by 2. Then take those results and add them to the numbers in row 2 and replace row 2 with that result. Okay? So this is called row operations on a matrix. All right, let's go down to another one. Here's some more where we're practicing how to do these operations on matrices. So this example says, go in here, take 1/2 times row 1's elements, and after you do that, put the results back into row 1. So again, we're going to be changing row 1. Okay, row 1 is what's ultimately changing. So we leave row 2 alone, and so it's probably a good practice to go ahead and write in the terms that are not going to change. Now the ones that are going to change is it says take 1/2 of row 1 and put those numbers back into row 1. 1/2 of negative 2 is a negative 1. 1/2 of 4 is 2. And 1/2 of 10 is 5. So that's my resultant matrix from doing what it has asked me to do. Now it wants me to take this matrix and continue with it by coming in here and taking row 1's numbers, add them to row 2's numbers, and put the result back into row 2. So now row 2 is changing, not row 1, so I'm going to go ahead and keep my row 1 the same before I come in here knowing I'm getting ready to change row 2. Okay, I'm going to take row 1 and add it to row 2, put those results in as my new row 2. All right, negative 1 plus 1 is 0. 2 plus 5 is 7. And 5 plus 3 is 8. Here's another practice for us. This is a 3-row, 4-column matrix. It's a 3x4 matrix. And it says, take negative 1 times row 3, take those numbers and add it to row 2, and the result of that addition, put that result in as the new row 2. So row 2 is getting ready to change. Okay, so row 1 will remain the same, and row 3 will remain the same, but row 2 is getting ready to change. Okay, so negative 1 times row 3. Negative 1 times row 3 makes us a negative 2, a negative 1, a negative 7, and 0. Add those numbers which I just wrote to row 2. Negative 2 plus 2 is 0. Negative 1 plus negative 8 is negative 9. Negative 7 plus 4 is negative 3, and 0 plus a negative 18 is negative 18. Okay, now what do they want me to do? Now they want me to come in here and take negative 1/9 times row 2, and whatever the result is when I do that, put the results back in as the new row 2. So I know that row 2 is changing, so I'm going to leave row 1 as 12, 0, negative 6, and 3. And I'm going to leave row 3 as 2, 1, 7, and 0, but row 2 is going to change. I'm going to take negative 1/9 times every element in row 2. In row 2. Negative 1/9 times 0 is still 0. Negative 1/9 times negative 9 is 1. Negative 1/9 times negative 3 is a positive 3/9, which is 1/3. A negative 1/9 times a negative 18 is positive 18/9, which is 2. Okay, so now we've learned how to kind of play around with the numbers in matrices. And now it talks about, here's the words, the reduced row echelon form, RREF, of a matrix, and also just the row echelon form, the REF, of a matrix. They show an example here. If you can get your matrix so that your diagonal is all ones, and then zeros are below the ones, this is the row echelon form of your matrix. If you do these row operations to the point that your matrix has all ones on the diagonals and zeros above and below those ones, then you have the reduced row echelon form of the matrix. We really like the reduced row echelon form of the matrix because if you look at this, converting it back to a system, this is 1x plus 0y plus 0z equaling 12.6. The second row would be 0x plus 1y plus 0z equaling negative 4. And the third row would be 0x plus 0y plus 1z equaling a negative 3.8, which are my solution values for my x, my y, and my z, which is what we want. That is what we want. So the desire is to take a matrix and get it into reduced row echelon form, because then we can take and know what the solutions are, what the values for each variable are. This process of all these row operations is referred to, well, it's usually Gauss-Jordan, but they're calling it Gaussian elimination. We call it the Gauss-Jordan method, which is called the Gaussian elimination process. Okay, don't worry about all those words, but you may very well see those words when you get into Connect Math. Okay, so here's an example. We're going to write this the equation, which is actually already in standard form. We're going to write it as an augmented matrix. Okay, so my augmented matrix are the coefficients, a 3, a 4, and a negative 32, a 2, a 3, and a 7. The goal is to figure out what the solutions are, meaning what is the value of x and what is the value of y that would satisfy both equations and be the solution to the system. But we're going to use a matrix. We're going to take the matrix, put it in reduced row echelon form, so we have our solution. Okay, so my goal is I want a 1 to be in the top left position because I want 1s down my diagonal. So what I think I'm going to do, and this is where you have tremendous freedom, I think I'm going to take row 1 and subtract row 2 from it, because that'd be 3 minus 2, making that a 1, and put those results back into row 1. Okay, so what I have written says that I'm changing row 1. After I've done all this, row 1 will be different. So row 1 is going to remain the same. Excuse me, row 2 is going to remain the same. Okay, so here we go. Row 1 minus row 2. 3 minus 2 is 1. That's a good one. We want 1s on the diagonals. 4 minus 3 is 1. A negative 32 minus 7 is a negative 39. Okay, now my goal is that I don't, let's see if I can get the highlighter. I want this to be a 0. That position highlighted, I want to be a 0. So what I'm going to do to make that 0 is I'm going to take negative 2 times row 1, add it to row 2, and put those results back into row 2. I'm going to take negative 2 times row 1, I'm going to add it to row 2, and put the results back into row 2. So my row 2 will be changing ultimately. So I'm ready for my row 2 to change. All right. So if I take negative 2 times row 1, negative 2 times 1 is negative 2. Negative 2 times 1 is negative 2. Negative 2 times negative 39 is going to be a positive 78. Is that right? Okay. Take the blue numbers and add them. Take the blue numbers and add them to row 2. Negative 2 plus 2 is 0. Yes, I want a 0 there. Negative 2 plus 3 is 1. 78 plus 7 is 85. Correct? Okay. So at this point, I've just got lucky and I have 1s on my diagonal. I have a 0 under my 1s. I want a 0 also above my 1s, which means I need that number that I just highlighted to be 0. All right, so to make that 0, I'm going to take row 1 minus row 2 and put the results back into row 1. So I'm going to change. Ultimately, row 1 is the numbers that will change. So I'm going to go ahead and write my matrix again with row 2 in place. Okay, row 1 minus row 2. 1 minus 0. 1 minus 0 is 1. Column 2. 1 minus 1 is 0. I got it. Column 3. And negative 39 minus 85 is a big old negative number, right? Is it 124? Okay. So at this point, I am in reduced row echelon form because my 1s are on my diagonal and I have 0s everywhere else. The last column you don't worry about. So now what I know is if I convert this back to an equation, it will say 1x plus 0y equals a negative 124. Yes.
85 positive? So
Yes, but I subtracted them.
Oh.
But thank you for checking it. I'm subtracting, right? So if I take negative 39 minus 85, it'll be even more negative. Okay, but thank you for checking me. Okay, and then the last row, 0x plus 1y equals 85. I now have my x and y value. I know the solution to this system. This is it. So I have solved my system of equations by using matrices. This is called the Gauss-Jordan method. Okay, and it's in reduced row echelon form. Echelon is spelled E-C-H-E-L-O-N. Okay, which is on the prior page. All right, now let's try another one. Okay, let's get better at this. All right, so my goal is what is my x value and what is my y value? And I really would like to have this, turn it into a matrix, convert it to reduced row echelon form, and bam, I have my solutions. All right, so my augmented matrix is 2, 3, 7, 3, negative 5, 1. and I've not been consistent at putting this little dashed line in. It's the numbers to the left of my dashed line that I'm most concerned with. I need a 1 in the top left corner. If I take 2 minus 3, it's a negative 1. So I think what I'm going to do is interchange my rows. Okay, I'm going to interchange my rows. And when I do that, I will have a 3, negative 5, 1, a 2, 3, and a 7. I'm going to interchange my rows. All right, and here we go. Now I'm going to take row 1 minus row 2, because that'd be 3 minus 2, giving me a 1 in that top position. Row 1 minus row 2 back into row 1. So ultimately, my row 1 is going to change. So I'm going to write the matrix again, leaving row 2 alone. Okay, row 1 minus row 2. 3 minus 2. 3 minus 2 is 1. Negative 5 minus 3 is negative 8. And 1 minus 7 is negative 6. I have my 1 in the top left corner. Now I want a 0 underneath it. I want this to be a 0. Any suggestions as to how to make that a 0? What do you think? There you go. Negative 2 times row 1 added to row 2, put back into row 2. I need to move left a little bit on my screen. Okay, so when I do this, note that it is row 2 that will change. So I'm going to move left just a little bit. So row 1 remains the same. And here we go. I'm going to take negative 2 times row 1. Negative 2 times row 1. This will be a negative 2 times 1, which is negative 2. Negative 2 times negative 8, which is a positive 16. Negative 2 times negative 6, which is a positive 12. I'm going to take those blue numbers and add them to row 2. Negative 2 plus 2 is the 0 I was wanting. 16 plus 3 is 19. And 12 plus 7 is 19. I have my 1 and I have my 0. Now I want the other diagonal to also be a 1. I want this 19, whoops, I didn't get my highlighter. I want this 19 to be a 1, so my diagonals are 1s. To do that, I'm going to take 1/19 times row 2 and put the results into row 2. So I'm only changing, the outcome will be a change in row 2. So leave row 1 alone. And row 2, 1/19 of 0 is still 0. 1/19 of 19 is 1, and 1/19 of 19 is 1. I have 1s on my diagonal. What number do I now want to change? There you go. This little guy here has got to go. Any suggestions about how to do that? Okay. How about 8 times row 2 added to row 1, right? 8 times 1 would be 8, and then negative 8 plus 8 would make it 0. And put these results into row 1. So row 1 is changing. Okay, so leave row 2 alone. Row 1's getting ready to change. Okay, I need to take 8 times row 1. 8 times 1 is 8. 8 times a negative 8 is a negative 60. Wait, I'm doing this wrong. Which wrong row, right? Lose that. Yeah. Okay, I don't like that either. I'm being kind of picky here. I'm making a mess. Okay, get my bracket back on here. Now I'm going to change it back to blue. Okay, here we go. 8 times row 2. 8 times 0 is 0. 8 times 1 is 8. And 8 times 1 is 8. So I'm going to take row 1 and add it to row 2. 1 plus 0 is 1. Negative 8 plus positive 8 is 0. There it is. Negative 6 plus 8 is 2. We got it. We are currently in reduced row echelon form. What is my x value? 1x plus 0y equals 2, right? And 0x plus 1y equals 1. Here are your solutions to the original system of equations. Okay, now, in general, we don't use matrix algebra or matrices on such a small system. We would usually have more like 4 equations and 4 unknowns in something like a 4 by 5 matrix that we're doing all this to. Okay, and it gets to be pretty intense, okay? You can have your page covered in matrices to solve one system, but that is so much easier than doing method of substitution or method of addition in a huge system of equations. So this would be something a little bit bigger, which is a 3 equation, 3 unknown system. And if I wrote this in matrix or as an augmented matrix, this would be a 2, a negative 6, a negative 1, and a 7. Then you'd have a 1, a 2, a 1, and a 0, a 1, a 4, a 2, and a negative 3. The goal would be to get this in reduced row echelon form. You understand? The goal would be to get all of these to be 1s, all the numbers underneath them to be 0s, and then the numbers above them to be 0s also. Okay? All right, it's a lot of work. Okay? It takes a while, and you have to be so careful, and that's why I said you tell me if I add something wrong, because you make one mistake and it blows the whole process. All right? So we want the reduced row echelon form of this. And what I'm going to do at this point is I'm going to show you how to do this on the calculator. Now, back in my day, we did this by hand, okay? But today we can do it on the calculator. Okay? So just briefly on this screen where I'm recording, what we're going to do is enter this big old matrix into the calculator, and we will have to enter it by dimension. And it's a 3 by 4 matrix, so you need to be sure you understand the dimensions of your matrix. You have 3 rows and you have 4 columns. So within the calculator, we're going to name this matrix Matrix A, which is a 3 by 4 matrix. Okay, we're going to name this matrix Matrix A, which is a 3 by 4 matrix. Then we will go to our home screen and we will have the option to use the RREF, the reduced row echelon form, the program in the calculator of this matrix A to get it in the form we need it in to give us our solutions. So whenever we do the reduced row form of this, reduced row echelon form of this matrix, it results in 1, 0, 0, 3, 0, 1, 0, 0.5, 0, 0, 1, negative 4. Now, then when you convert it out of the matrix back to an equation, this is 1x plus 0y plus 0z equaling 3. Row 2 is 0x plus 1y plus 0z equaling 0.5. And row 3 is 0x plus 0y plus 1z equaling negative 4. Here is your solution to your system. Yay is right. Okay, so now if we want to practice it again, and we have just enough time to practice it one more time, let's look at this last example. My augmented matrix will be 1x, negative 1y, 5z, negative 6, 3x, 3y, negative 1z, 10, 1x, 3y, 2z, and 5. So this will be my matrix, and if you want to name this one matrix B instead of matrix A, you can, whatever you want. I think I'm going to stay consistent with matrix A. What are the dimensions of this matrix? A 3 by 4. You have to know that because you have to tell the calculator the dimensions before you can put it into the calculator. So if we want to name this matrix A, we will be taking the reduced row echelon form of matrix A to ultimately get our solutions. When we do the reduced row echelon form, we come up with this result on the calculator. So ultimately my x value is 1, y is 2, and z is -1. Don't we love calculators?